All right, hey everybody, I'm Kristen.
I'm Ritesh.
I'm Sunny.
I'm Sajna.
And I'm Zach.
And today we're going to talk about part 2 of the experiment you just heard, which is the high-resolution powder X-ray diffraction at beamline 1117 BM at Argonne. Okay, so you just heard from Charles, Berkeley, and Nathan about the data output that you get from these experiments, which, as we can see, these nice rings. This is due to the polycrystalline material being ideally oriented in a completely random orientation. And what we do with this data output is followed by the structure solution. And it's important to note that today we're not actually going to be talking about structure solution, we're talking about the refinement. So I've listed here a couple of the software systems that you could use to do the structural refinement or structural solution. But today we're just going to talk about RIETVELD refinement, which is the refinement of the model that you get from the structure solution. So this is just a typical data set that you might get. This was ours of the copper oxide going to copper metal experiment that we did. And this is actually this is the data set that we took at room temperature. And what we do is we fit it to the model. So we used a program known as GSAS2, which you've probably heard of. And basically it fits a model which it thinks goes with your data set. And then what you have to do is sequentially refine it. So to relate this to the experiment that we did, we carried out a reaction. I've shown the equilibrium reaction here, but we were actually carrying out the backwards reaction. So we started with copper oxide, and then we reduced it to copper metal with carbon monoxide. And we started at room temperature and ramped to 300 Celsius. And here I've shown a plot of intensity versus 2 theta of all of the images that we took. And we're taking these at 10 degrees, we're taking this at 1 image per minute and every 10 degrees. So here you can see from the actual powder pattern how it changes with the structure and the temperature ramping. By simply manipulating that plot and looking at it top down, you can see that the data sequence, which is on the y-axis, is just the temperature. So as the temperature increases, we're going higher up in our image number. 2 theta is still on the x-axis, and the intensity is displayed as the color plot. So here we can actually see, as the last group showed, this is the copper oxide that we have at low temperature, and as it heats up to higher temperature, we get the formation of copper metal. So at this point, we can start our refinement.
Okay. So the next step is the RIETVELD refinement. So now that we got the 2 different phases, we need to analyze the data. We can determine the phase of the individual structures, which is the copper oxide and copper, by looking at the Miller indices and doing a pattern match from the database. But to do a quantitative analysis of the mixed phases and to completely validate the structure, this RIETVELD refinement is used to do this process. So RIETVELD is basically a least squares analysis method that minimizes the difference between the experimental pattern and the model that is obtained from the database. This is kind of similar to like a linear regression plot or for curve fitting or a linear fitting, where you try to minimize the difference, the distance between the individual data points and the actual curve itself. So as we do the refinement, we change some of the individual parameters, and the goal is to go to the global minimum, which is actually the best fit. At some points, we can also go to the local minimum, and we can also make false conclusions, as we did, and you'll hear soon about that. The other parameters that also are important to follow RIETVELD refinement is the profile residual, which is the RP value, and I describe the profile residual as the difference between the observed and the calculated data points. And this value should generally be less than 10% to say that we have a good fit. And the weighted residual profile is another parameter that also does the same thing as the first, as the profile residual, but also pays attention, weighs the higher intensity peaks reflections over the lower intensity ones. And the goodness of the fit is the RWP divided by the RXP, and that's also measured to follow the refinement. So this is the general strategy to follow a RIETVELD refinement. So we first fit the lattice parameters, the peak positions and intensity and shape without including the atomic position, atomic displacement. And this is known as the Lebel fitting. And the next, we also include the atomic positions and displacement and thermal parameters and under this RIETVELD refinement. And so the general strategy is we continue to run cycles until we get the lowest RWP value. This is an example of a good fit, a refinement fit. So this is a structure with the red dots represent the calculated pattern, which is overlaid onto the experimental pattern. And as you can see, the residual parameters are much less than 10%, which indicates it's a good fit. These ticks represent the peak positions, the 2 theta positions for the phase. And the green represents the difference between the calculated phase and the experimental phase. And as you can see, it is pretty much a straight line, indicating they're very similar. And next,
now we began the actual fitting process. To do the label fitting, we first need the initial structure. And there are some databases for the diffraction pattern, like inorganic crystal structure diffraction and powder diffraction file database. We know that each material has its unique diffraction pattern, and based on the experiment results, we compare its peak position and the relative intensity to find the initial structure from the database. And now we can get this fitting value. Our goal is to match the fitting to the experiment. And we first adjust the overall intensity. And the label fitting is mainly about the unit cell. After we choose the phase, we have fixed the space group, and now we want to refine the lattice constant to match the peak position. And after that, we can say that the R value is still very large. And the next step is to refine the scale factor. Scale factor is the individual contribution of different phases to the overall diffraction pattern. And we know that despite the signal from the sample, there are some signal from the background. So we need to refine the background. We use a fifth order polynomial to characterize the background. And after this step, we can reduce the R value to 30%. And we have refined the peak position. The next step is to match the peak shape. We use the pseudo weight function, which is a combination of the Gaussian and Lorentzian function to match the peak shape. And Sanjana will talk about it.
So once we refine the peak positions, you can see that the RWP factor is still pretty high. And you can also see that the blue ticks, which are the actual data, is still sort of above the actual fit that we got. And what we can see from this is that probably the peak shape itself is not right. So what are the factors that influence the peak shape? One of the factors is finite crystallite size, which can lead to broadening of the peak. And there's also the possibility of microstrain existing in the powder, which can lead to a broadening of the peak as shown in the figure. If you have a homogeneously strained crystallite, you can see that the despacing basically either reduces or increases, and this just shifts the peak a little bit. But if there is an inhomogeneously strained crystallite, then it basically leads to a smearing out of the Bragg peak, which you can see as a broadening in the peak basically. So in order to fit this peak shape, what we use is the combination of a Gaussian and a Laurentian, which is basically the pseudo-void function that Shen mentioned. And this actually reduces the RWP factor by a huge amount, which is 15.6%. And you can see that the fit is much better than what we had before. Now, this is followed by a final structure refinement, which basically includes refinement of the atomic positions with respect to the lattice sites and also the atomic thermal displacements. Now, as Ritesh mentioned, this is the only factor which distinguishes the Libel refinement and the RIETVELD refinement. Okay, so now that we have seen how to actually basically reduce one single data set to something meaningful, what we want to do is make sense of the entire experiment by actually fitting all the data sets that we got from the experiment. And in order to get something physically meaningful, we would want to avoid overfitting, and that is what Zach is going to talk about.
Thanks. Okay, so I'm going to bring us back to this counter plot here. What you'll notice is that, as we said before, the copper oxide comes in from this direction while the copper comes in from this direction. And you can actually refine from either side as long as you have the CIF file of the copper oxide to start down here and the CIF file of the copper to start up here. However, every point in the middle is going to be just a tiny bit different. And so what GSAS can do is actually refine large sections of your counterplot all at once. The problem is this overlap region here. This overlap region is going to be a little bit more complex, and if you try to do it all at once, you're going to notice that you either don't converge or, in our case, converge when you're not supposed to. The way that you do or handle this region is you split it up into 4 different sections of weak and strong patterns from each. You come from one direction. In particular, we started with the copper oxide direction, and then we get to this point where you just see the copper pattern start. There's a little bit of a change in the shade of the blue there. That's how you tell. And then we refine from the other direction as well. Again, it's not really important which one happens first, but there are more patterns down here to refine. And so then you take the parameters that are in common between all of them. You copy them to these regions, and you refine from weak to strong or weak to strong. I didn't add an arrow for that because it doesn't really matter which direction you go in. However, after you do that, you want to go into the intermediate region here and attempt to refine that. Again, this is a long, arduous process if you were to do this one refinement at a time. That's what GSAS excels at. Finally, you want to go across the entire thing and make sure that everything is self-consistent. We didn't do every single one of these sequential refinements. However, the one that we did in this area gave us a pretty good weight fraction component. However, this was a parameter that we restrained before we did the sequential refinement. So it was bound to give us something that looked like it made sense. However, when you look at the weighted profile R factor, you see that there is a huge deviation. This area might make you think that there's some sort of pattern. However, this is the weighted R factor, so the lower is actually the better. And since we can see that this is lower, it's more likely that this one was actually the correct one, and the other 3 were us finding a local minima that wound up keeping us there in a way that the refinement could not pull itself out of. And in conclusion,
to summarize our high points, we found out that Rietveld refinement is a pretty useful method for refining a model that we can use to fit to our data. We start with a Lebesgue fit, and this only requires that you have a space group and a unit cell, which you refine, and then you carry out the Rietveld refinement in order to account for the atomic displacement and thermal parameters. And finally, we performed a sequential refinement so that we could watch how the structure of copper oxide changed and how it changed into copper metal over the course of heating. And we were able to quantitatively determine how much of the phase was in the copper oxide phase and how much was in the copper metal phase. But one thing to keep note of when you do these Rietveld refinements, as Zach was just talking about, is to make sure that you don't overfit your data, because you can fit anything and you don't want to be led to the wrong conclusion. So with that, we'd like to thank the NXS School, all of our directors and organizers. We'd like to thank the Beamline scientists that help us with this experiment, the DOE for funding, of course, and all of you. Thanks. So we actually do see that very slightly. I'm not sure if it's easier seen here. So if you notice, there's like a very faint peak right between these two copper oxide peaks, and that is actually a very minute amount of the copper 1 oxide forming, and then quickly disappearing before it is it turns into the copper metal.
Up at the higher temperature regions of your plot, it looks like you're actually losing some of the copper. Is that real? Do you know what's happening to the copper up in those upper temperatures?
So what we ended up finding, and I think that this was simply user error and maybe a factor of heating or cooling too quickly, but we ended up seeing the conversion of the copper metal to an amorphous copper compound. So that's why you kind of see this shady region up here. But ideally, it should have just gone to copper metal.
So you did a good job of saying, basically kept getting a better REFINEMENT fit and reducing your percent by adding more parameters. And so do you know how many parameters did you end up with? And what limits that? Like, I assume you don't have vacancies in there or other
Right.
more complicated things. So how many parameters can you put in and how many did you have?
That is certainly a sample-dependent question. For ours, I think we ended up fitting 6 parameters or so. We did atomic displacements, thermal parameters. We accounted for things like microstrain and crystallite size. So 4 or so, plus a couple that I'm sure we're forgetting.
The actual number, it sounds like more than 6. Like thermal displacements could be in the list.
Right.
3 for each
Right.
atom and everything. So, but I think basically the limitation is the number of peaks you get. The more peaks you get, the more things you can fit.
Exactly, yeah. The more complex your structure, the more distortions and vacancies you have, the harder it is to fit. So the more parameters you have to refine.
You should understand that the REFINEMENT method handles overlapping peaks very well.
Yes.
So you can have multiple phases and refine their weight fraction very easily directly.
Mm-hmm.
So in that 2-phase region, you have no problem with refining how much of each phase.
Yeah, it actually took us about less than 5 minutes to do the sequential refinement versus having to go through frame by frame and carry out the entire refinement for each one. So apparently GSAS is really good at this, so good software.